So this is a paper that just came out that actually looks at the embedded emissions in actually transitioning to the pathways that we want we have set either based on global warming targets or decarbonization and so on. And the transitions like the implementation of renewables, for example, or adaptations like protecting against sea level rise or moving people away from coastlines takes a lot of materials and energy, and it will result in emissions. So the analysis here shows that the rate of transition actually can increase or decrease the embedded emissions in the transitions themselves in terms of mitigation and adaptation. So it's worth just looking at the concept itself. Of course, the results depend on a model, which means they come with their own uncertainties based on the assumptions that go into these models. But nonetheless, the significance of the results, as the authors themselves report, are adapting to increasing climate risks while deploying renewables to stabilize the climate will require large amounts of energy and materials, which will initially cause emissions, obviously. We provide an estimate of the CO2 emissions embedded in this broader climate transition, which were previously poorly quantified. Fossil fuel energy used to deploy renewables contributes the vast majority of embedded emissions, with a much smaller contribution from adaptation. As a result, embedded emissions increase substantially for slower decarbonization pathways. This is critical. How we transition, how rapidly we transition can determine these embedded emissions. However, when renewables are rapidly deployed, the ongoing transition can be powered by cleaner energy. So if you go slow and the renewables are not meeting the demands of replacing the fossil fuels in addition to providing for the transition, then you increase embedded emissions. Whereas if you do rapid transitions and the renewables grow substantially, then they themselves can be used for the transition. The ongoing transition can be powered by clean energy, minimizing embedded emissions. Our results demonstrate an underappreciated benefit of an enhanced climate ambition and the importance of accounting for embedded transition emissions to achieve climate objectives. And the paper looks at decarbonization pathways along these. So transition interventions in terms of quantity of measure, embedded energy, and embedded emissions are looked at for deploying renewables, adaptive space cooling, and coastal adaptation. Okay, space cooling of course can include buildings, transportation, and chilled path transportation logistics of storing meat and vegetables and fruits and transporting those things and so on as well. So things being looked at: net sustainable energy transition model plus carbon budget simulated in the NetSet model. In the adaptive space cooling, energy demand generator edge and then warming projections are required. And in the coastal adaptation, coastal impacts and adaptation model plus sea level rise projections and life cycle analysis are used. And for the emissions factors from life cycle analysis plus energy mix from the NetSet projections are looked at. The rubric of estimates reported and summary of underlying methods in this paper consider decarbonization pathways as gradual, rapid, and delayed, with multiple pathways used in IPCC AR5, for example, RCP 2.6, 1.9, and 4.5, representative concentration pathways. If you don't know what they are, you can look at my other podcasts. And the scenarios from IPCC are called sustainable development, which are also mapped onto the so-called shared socioeconomic pathways, or SSPs, which are used in the assessment report 6. Ambitious scenario to meet Paris Agreement 1.9, which is 1.5 degrees C by 2100, most ambitious one, and the intermediate scenario, which will take us to 2.7 degrees C. You know already probably that this 2.6, 1.9, and 4.5 refer to the additional energy being trapped by the system because of greenhouse gas increases by 2100 in terms of watts per meter squared. Okay, so the remaining carbon budget, which comes from the fact that the additional warming is going to relate to accumulated carbon along the way, so you can estimate how much carbon is left to reach these targets, and then look at the difference from where we are in 2020, where the paper considers the historical period. Everything after that is projection. So obviously for a lower target you have lower room, so 1150 gigatons CO2 for 2 degrees C, only 400 gigatons for 1.5 degrees C, and 2150 gigatons for 2.7 degrees C. And the results, I won't go into the details, but there is basically estimate that is required to build the renewables and the transition, and then there is some energy required to maintain them. So that's what gives you this black line called net, and these consider historical periods for concentrated solar power, photovoltaic, winds, geothermal, gas, oil, coal, biomass, other, and biofuels, nuclear, and hydro. And when you do gradual energy decomposition pathway, obviously the contributions from coal continue. For example, coal is this color here, will continue longer than you would want. So you're burning coal here even into 2060 in terms of meeting the primary energy demand in exajoules per year. And the contributions from wind, solar, and so on will increase only after 2040, 2050, and so on. So you will continue to burn fossil fuel like gas, oil for much longer than you would like. And of course, coastal protection, where segments correspond to the heights. I won't go into the details of how they are defined, but optimal protection height is going to be determining the cost and the embedded emissions as well in this pathway with the decarbonization rate assumed. So you can see that you are going to also impact the coastal retreat in terms of percent of coastal segments and the optimal retreat population. These are all projections based on SLR and the life cycle analysis and so on, keeping in mind the scenario RCP 2.6 and how much carbon is left. So you're basically looking at how much the transitions themselves will contribute to chewing into the carbon budget left to stay under this target of 2 degrees C under RCP 2.6. So here you have global mean sea level rise projection, and then the global mean cooling degree days per year in terms of thousands, so kilo CDD here. So you can see that kilo CDDs are expected to increase and sea level rise is expected to increase. And of course there are details that global mean sea level rise will not have much meaning at local levels, plus how much you can protect against instead of sea level rise will depend eventually on the finances available. For example, if Mumbai expects 1 meter sea level rise by 2100, can it really afford to build against 1 meter sea level rise, or will it only be able to afford 20 centimeters or 30 centimeters based on how much investment it can make into the future to protect against the sea level rise. Nonetheless, the main goal here is to keep our eye on the energy demand and the embedded emissions that go with it based on the decarbonization pathway. So looking at embedded energy per transition measure, this looks at deploying renewables using fossil fuel in exajoules per year. So here you are, the pathway and the meeting of the energy demand. As of now, we are coming out increasing our deployment of renewables, which are expected to peak at some point, but the weaning out of the deploying the embedded energy transitions from fossil fuels have to drop, and adaptive space cooling is going to increase in demand in terms of exajoules per year, because that corresponds to the number of cooling degree days that are expected to increase along the way as well. And here are the 2060 estimates of coastal protection actually going from 2020 to 2100 in terms of energy demand and coastal retreat. Transient numbers are not given for those two. It doesn't matter. But just notice how quickly we drop the fossil fuel dependence on deploying renewables is going to determine the embedded emissions. If you look at deploying renewables in terms of embedded emissions instead of energy demand, here is where you end up. So if you rely on coal, you can obviously expect coal burning to go on for a long time and contribute to embedded emissions, and oil, and then gas. So you have to obviously phase them out at some point. And you can look at deploying renewables in terms of total embedded emissions contributions in gigaton CO2 from coal, oil and gas, and the total. So this is the percent of carbon budget, keeping again in mind the room left to meet the target. So adaptive space cooling embedded emissions will drop along the way as we increase the renewables for driving adaptive space cooling as well along the way. So here are the gigaton CO2 per year from that. If you look at sea dike emissions, again, various contributions in terms of kilogram CO2 per meter cube. So make sure you know the difference. These are emissions and these are embedded CO2 in terms of the amount of matter used, concrete and the processes, steel and processes, concrete and energy, and steel and energy. They drop, but the question is how quickly can we make them drop, right? So this is resettlement emission factors, similarly in terms of processes and energy related. So obviously there are a lot of assumptions involved here, because there are separate estimates of how concrete and steel themselves can be driven towards decarbonization or reducing emissions, because they have some so-called irreducible emissions and so on. So I have separate podcasts on how to reduce emissions from those industries, which also go into these calculations, but not necessarily mapped in calculating these in these models. So we do all these things separately. So adaptation total embedded emissions in terms of adaptive space cooling and coastal settlement and protection go from in this direction. So gigaton CO2 to protect, to retreat and cooling. So this is the total, and that's the percentage of carbon budget that gets used up when you do this. If instead you use rapid energy decarbonization pathway and aim for RCP 1.5, 1.9 with limitation of warming to 1.5 degrees C with a 67% probability by 2100, then you can see that you will be phasing out coal, oil and gas very rapidly compared to before. You'll be increasing the contributions of wind and solar very rapidly, as well as adding more of the biofuels, nuclear and hydro. Okay, that's in terms of meeting the primary energy demand for decarbonization pathway for this scenario. Whereas if you delay the decarbonization pathway, you will head towards RCP 4.5 with 2.7 degrees C warming by 2100, and then you will have obviously much more reliance on fossil fuels with much less contribution to meeting energy demand for the transition from renewables. So this is again going to increase the embedded CO2 emissions from coal, gas and oil, and you will use much more of the remaining carbon budget. So you can look at it in terms of the remaining carbon budget percentage used by each pathway. So for the rapid transition, you can do the transition with only 5.2% of the carbon budget being used in embedding the emissions into transitions. If you go gradually, you're going to up it to 8.2% of the carbon budget, whereas if you delay it, you will jump to 8.4%. But of course, there are other externalities of air quality in terms of impacts on human health, agriculture, sea level rise, and so on and so forth. If you look at embedded emissions from adaptation 2020 to 2100 totals, again from cooling for rapid transition, drivers of change here, this is from gradual and this is from delayed. So you will get emission intensity increase and the amount increase based on how fast or how slow you go. Okay, so to summarize, basically total embedded emissions in the transition relative to the 1.5 degree C remaining carbon budget, total embedded emissions from deploying renewables and selected adaptations over 2020 to 2100 for the three decarbonization pathways expressed as a percent of the 1.5 degree C remaining carbon budget, which is 400 gigatons CO2, but this number has some uncertainties in them. Nonetheless, rapid transition will give us embedded emissions as a percentage of 1.5 degree C target of 5.2, as we saw. Gradual will jump it to over 20%, and for delayed we will chew up close to 50% of the remaining carbon budget in terms of embedded transition emissions. Okay, so what do you do with it? Just think about how much we have to worry about not only decarbonization but how we get there. How do we get there? So one way to think about it is that we have enough fossil fuels to transition, so fossil fuels eventually have to remain in the ground, but how quickly we transition and how quickly we phase out fossil fuels is going to determine how much of the remaining carbon budget we're going to use up along the way. Obviously, we want to use up as little as possible as we go along, just to account for the uncertainties like geopolitical perturbations, like the Russian invasion of Ukraine has caused a lot of energy use problems and reliance on fossil fuels, including coal for winter heating in Europe, for example. And of course, there are also events like the pandemic, which can create temporary dips in emissions, but then you recover very quickly because economies slow down and governments want to stimulate economies by spending without worrying about emissions. So all these complications have to be worried about when we try to minimize the embedded emissions in the transition itself. Okay.